Higher physics, particles and waves, interference and path difference. Key areas. Conditions for constructive and destructive interference. Constructive and destructive interference in terms of phase between two waves. Coherent waves have a constant phase relationship and have the same frequency, wavelength, and velocity. Interference of waves using two coherent sources. What we will do today. Revise some basic wave definitions from National 5. Use correctly the terms in phase, out of phase, and coherent when applied to waves. Explain the meaning of constructive interference and destructive interference. State that interference is a test for a wave. And state that reflection, refraction, diffraction, and interference are characteristic behaviors of all types of waves. Phase. Two waves are in phase, as seen in the diagram. The maximum and minimum points on the wave occur at the same time. Note that the waves have different amplitudes, but can still be in phase as long as the peaks and the troughs of the wave meet. Here, we have two waves completely out of phase. The maximum points of one wave occur at the minimum points of the other wave, and vice versa. Coherent sources. If waves coming from two sources have the same frequency and a constant phase relationship, they are said to be coherent. Coherent waves coming from a single source will have the same amplitude and so undergo completely destructive interference. This is a common question within the CFE Higher Physics course, as shown here in the specimen paper. We're asked to state what is meant by coherent light. All we need to state here is that the waves have the same wavelength or frequency, speed, and they have a constant phase relationship. Wave characteristics. Reflection, refraction, diffraction, and interference are characteristic behaviors of all types of wave. They can be considered as the tests for a wave. We have previously covered the first three in National 5. Reflection. Waves reflect off a surface. The angle of incidence, that is the incoming angle, is equal to the angle of reflection, the outgoing angle. And we looked at this when we were looking at Snell's law. Remember that the angle of incidence is measured between the normal line and the incident ray. The angle of reflection is measured between the normal line and the reflected ray. We can see from the diagram that the incident angle and the reflected angle are equal. Refraction. In refraction, waves change speed, and usually there's a change in direction, unless the incident ray is going in at 90 degrees to the surface, that is along the normal. The definition of refraction is the change in speed of light when moving from one medium to another. Diffraction. This is the bending of waves around an object. Waves spread out around corners. When passing through the gap, the waves appear to curve. If the gap is similar to the wavelength or less, then the circular wavefronts are produced. As the gaps widen, the curve will lessen, and the waves coming out through the gap will appear flatter. Obviously, if there is no object in the way, if the gap is very, very, very large, then there will be no noticeable diffraction and the waves will appear completely flat. Interference. When two sets of waves meet, they combine to produce a new pattern. This is called interference. The new pattern depends on the original wavelengths and amplitudes. Waves can combine in one of two ways, either constructive interference or destructive interference. At higher, we need to be able to state that interference is a test for a wave. In constructive interference, we have two waves meeting in phase. That is, the peaks match the peaks, the troughs match the troughs. As the two crests meet or the two troughs meet, they produce a larger crest or trough, hence a larger wave. And that's where the term constructive comes from. In destructive interference, we have two waves meeting out of phase. If the amplitudes of both waves are the same, then this will cause them to be cancelling out each other. We end up with no wave at all. Two sets of waves meet completely out of phase, that is 180 degrees out of phase, where the crests meet a trough, and then they combine to cancel each other out and produce no wave at that point. Note, however, that if the waves are not of equal amplitude, then complete cancelling does not occur. When considering interference, we should look at the path difference between waves coming from two sources. An interference pattern is more easily explained in terms of path difference. Consider an interference pattern produced by two coherent wave sources, as shown on the next slide. Here we have source A and source B. The path from A to C and the path from B to C are equal. So the two waves travel an equal distance. There is no path difference. Therefore, the waves are going to meet in phase and a maxima is going to be produced. If we move along the screen to a new point C, we can see that the waves are now traveling different distances. There is a path difference between A to C and B to C. The path difference itself can be calculated from the difference between the two lines. That is, path difference is equal to BC minus AC. Once the path difference has been calculated, it can be compared to the wavelength of the waves. If the path difference is equal to a whole number multiple of lambda, that is, no path difference, lambda, 2 lambda, 3 lambda, then constructive interference will take place, because the path difference is as such that the peaks of the waves will match up. They will be in phase. The rule for this is for constructive interference, path difference is equal to m lambda, where m is an integer, 0, 1, 2, 3, etc. If the path difference is equal to a whole multiple of lambda plus a half, i.e. half lambda, 1.5 lambda, 2.5 lambda, then destructive interference will take place. The rule for this is that for destructive interference, path difference is equal to m plus a half lambda, again where m is an integer, 0, 1, 2, 3, etc. In the next video, we'll look at path difference in greater detail.